bit of time. I can talk about the lab or that we're going to do the next Thursday, I think. Next Thursday, yeah, Thursday the 11th. And it looks like, show this to gallery. I don't think I've handed this one out yet, but it's we're going to determine the molar mass of benzoic acid using freezing point depression. Remember, freezing point depression is a colligative property, which means that we could do this procedure with benzoic acid, or we could use some other compound, and it would produce similar results, but the outcome would be we could use the outcome to determine the molar mass of that molecule, regardless of what it is. Okay, so let me put this up here, Kim. 104L, and this is lab number 1. I abbreviate molar mass molecular weight of benzoic acid by freezing point depression. Okay, let me put that up in the, let me share that one. Stop this. Oh, did I lose? I think I lost Shania. Okay. So the whole idea, if we're going to determine the freezing point, the molar mass of any compound, we need to know 2 things. We need to know its mass, and then how many moles does that mass represent? And there's your moles. So we got to do the mass and the moles. The mass is easy because we're gonna weigh out some of it when we put it into the mixture and determine the freezing point. The moles is where we're using this concept, freezing point depression. The freezing point depression is determined by this equation. You remember from chapter 11, I think it was. So let's see, temperature, change in temperature, and we're going to use absolute because it doesn't matter the sign. Change in temperature for the freezing points is equal to Van Hoff correction factor times the freezing point depression constant for the solvent, okay? And then the molality of the solute in the solvent, okay? So this is where the moles is hiding in that term. So we're going to conduct an experiment where we put benzoic acid, that's my abbreviation. Actually, we determine the freezing point for the solvent, which is lauric acid. It's a fatty acid. I'll abbreviate that La. So we're going to do the freezing point for lauric acid, and that's going to equal a value. Then we're going to do the same experiment and find the freezing point for lauric acid plus benzoic acid. Right? And those will give us values. Let's say this one is freezing point depression. So this value is going to be lower than this value. I think ice cream churn. Like water freezes at 0 degrees, but when you add salt to it, freezes at a much lower temperature. Freezing point depression. So we're gonna get an initial temperature here. Let's see. This is yeah, we call that initial. And then a final temperature here with this experiment, freezing point. And then we calculate the delta T here and just take the absolute value. Okay, now we need I. So what is I going to be for a fatty acid? It's going to be 1. Right. So we can throw that one out. What's the K for the freezing point depression? Well, it's given in the pre-lab question right there. 3.90 degrees C per mole. 3.90 degrees C per mole. Now the units there it gives are kilograms per mole. But kilograms per mole is moles per kilogram. Right? So if we flip the kilograms up, that's kilograms on top, moles on the bottom. And that's fine. Why don't we do it that way? We'll put kilograms up here and moles down here. Because we're after moles anyway. Okay, so then the molal value is here. So the molal is moles of solute. In our case, it's benzoic acid per kilogram of solvent or lauric acid. Right? And this is going to be an unknown. We'll know this value, right? Because we're going to weigh out our lauric acid too. We're going to weigh out the benzoic acid, it goes here. We're going to weigh out this lauric acid, so it goes into this formula, and that becomes our unknown. Because this experiment will give us that value. That's a constant. We know this value, so our unknown is moles, and we can solve our equation for moles and put the value in right here and calculate the molar mass. Okay. All right. So there's a pre-lab question. Let's solve that one. See, I'm going to leave this stuff here and try to squeeze it in this section. So 7.98 grams of lauric acid. That's the solvent. So the mass of lauric acid equals 7.98 grams. Well, if we're going to put it down here as kilograms, why don't we just change it? 7.98 times 10 to the minus 3 kilograms, right? The unit got bigger, so the number had to get smaller by a factor of 1,000. That's why I did that. And it freezes, its freezing point is 43.75. This must be a fancy lab. You can get 2 decimal places out of your thermometer. The mass of the benzoic acid then, once we add benzoic acid to this solvent at 1.03 grams, 1.03 grams, plus the lauric acid. And that freezing point now is going to be less at 39.43. Okay. All right. So the accepted value for benzoic acid is 122 grams per mole. So let's plug in those values here. What's this value? It's 43.75 minus 39.43. Right? Let's see, 43.75 and 39.43 subtracted. So this value is 4.32 degrees C. This value is 3.90 degrees C, kilogram per mole. And this value is our, let's see, moles of benzoic acid over, what's the kilograms? 7.98 times 10 to the minus 3 kilograms of lauric acid. And now we can solve for moles of benzoic acid. All right, so this one is going to be divided by that one and then multiplied by this one. And let's see, I want more decimal places than that. Let's see. Here it is, display. Let's do scientific. And do 6 decimal places. There we go. I'm going to do it again. 4.32. Yep. 3.90 divide and times 7.98. There we go. So the moles of benzoic acid then, did you get it? You didn't do it. Okay. 8.839 times 10 to the minus 5 moles. Okay. So we can calculate now the molecular weight or molar mass as grams per mole. Grams. Here it is. 1.03 grams. And then moles is 8.839 times 10 to the minus 5 moles. So 1.03, flip that and divide. And I get 116 grams per mole. See, is that right? Yeah, 3 significant figures. That's all I got. Okay. Now, it doesn't say to do this, but what's the percent error? Remember the percent error. In the denominator, we want the accepted value, 122 grams per mole. And in the numerator, we want the difference between those two. Now, if we don't care which direction it's off, then we just take the absolute value of the difference. But if we do care how much it's off, we want to say the accepted value, no, the calculated value minus the accepted value. That will give us a negative number, and that tells us that the error is negative, right? This value is less than that value. You can do it either way. So 116, 122 subtract, and then 122 divide times 100, sorry. 100. So that gives me 0.49%. Do that again. It looked right. It's minus 4.9% error. Yeah, 4.9%. Okay. Just, it's not bad for a student lab. I wouldn't want to try to publish that in the referee journal. Okay. We have 2 activities here. One is the freezing point of the pure solvent. And then the second activity is to repeat the same procedure with the solution. Okay. It's a very simple procedure. We're going to have, all right, when you prepare your notebook, since you haven't done this in my class before, when you prepare your notebook, you got that handout with the series of things that I'm looking for. Yeah. Starts off with title, introduction, safety concerns, materials. Right? Yeah. And it's in. Yeah. Well, you got the sample notebooks in here. Okay, yeah. That'll show you the order of things that go in there. Now, on the day of the lab, there are things that you have a section line laid out for information, and you're not going to have anything in it. I don't expect anything in the data section. Calculation section would only have this type of calculation for your pre-lab question. Then you're going to have the data, then you'll have calculations. You have the procedure, of course, you write out the procedure in steps. And then you're going to have, are there any post-lab questions in this one? Okay, that's data and calculations there. Yeah, we do have some lab questions at the end, 3 of them. So you would just set up a section on lab questions or post-lab questions, and you'd have 1, 2, and 3. If it was me, I'd write out the question and then leave a space to put the answer. That way, if anybody looks at your lab notebook and you have post-lab questions with answers and no questions, it doesn't mean much. So if you write out the question, then whoever inherits your lab notebook can tell what you were talking about. So those things only have space reserved. For the data section, I would probably set it up so that I have empty spaces where numbers or observations are supposed to go. And it would be good to, this is a condensed version right there. That's a condensed version. In order to get the freezing points, you need space in there in your data section. Let's erase this. For values. If you look at your method, you're going to see that you're going to start off, say, for lauric acid first. You're going to have time. And I think it's how many seconds you go? 30 seconds is it each, I believe. So many seconds, start off 0, and you have temperature. And you put a value. And then you go 30 seconds, and you put another value. And you just keep going. And set it up so that you have your time set up here and blanks on this side for your values. Okay. And then you would do that for lauric acid plus benzoic acid, separate table. That way, when you start filling in, that way you also reserve space in your notebook in the logical sequence for this information. And if you get into the experiment and you start timing it and taking temperatures at intervals, and you get down here and you think you're putting numbers in at 120 seconds, but you look up here and at 90 seconds, there's a blank. It's like you skipped a space. Then you need to ask yourself, can I go with the data as is? Can I just cross through that and initial it? Or do I have to go back and start all over again? So that's the advantage of having tables and spaces set up for information that you're expecting to get. It kind of keeps you from wasting time. You know you're supposed to have values there. If they're not there, then stop. Say why. And if it's okay, then go ahead. Okay. And that's what I'm looking for. On that 11th, I want to see, is that right? Yeah, today's the 4th. That'll be the 11th. On the 11th, when we go in the lab, I'll check your notebook and see if you've got all that stuff in there. And great. If everything's in there as should be, then that's 100. I usually set minimum at 80. If you get less than 80%, I have students, you just sit there and watch. You don't get involved because that means that you're not ready. If you're not ready for the experiment, then you're just an accident waiting to happen. Okay, any questions? I'm sorry? Okay. So the sample notebook is actually, it probably has data in it. But it does show you the order. And at the end of the semester, I'll take one last look at your notebooks and see if it's got everything in there that it's supposed to have. Okay, this is a real simple experiment. All we have really is boiling water. Now, when you're weighing out the samples, lauric acid doesn't smell bad, but when you open that container of benzoic acid, don't breathe deep. It stinks bad. I don't know how hazardous this is. You'd probably have to stick your nose down there and snort it to be any problem. Okay. And the laboratory questions, those you answer on your own. They should be fairly easy to manage. Sometimes in some of our lab experiments, the post-lab questions actually involve doing parts of the experiment itself, like how you treat the data. So if that's the case, and you answered that question in some other part of your report, then when you write your formal report and you put that question in there, you can say, see, such and such. You don't have to duplicate all the stuff. And that one, I noticed you had on top that copy, common errors. Yeah, pay attention to that because students lose a lot of points with those simple errors. One biggie is when you write the report, you change the tense. When you write it in your notebook, you're saying, this is what I'm going to do in the future. This is the instructions for doing the experiment. When you write the report, you say, this is what I did. So the tense of your sentences changes.